Hey everyone. So screen is not being shown. Okay. Yeah. Okay. This video is about the task which I asked you. So I had asked you record your voice on MATLAB, read it, and observe the spectrum. Okay. So let us try it today. Okay. So the command in MATLAB to read the audio that you record is audioread. Okay, so there are many. Okay, so on extreme left top corner, right top corner, you can search always. So I found this cool audio read function. Okay. So should we do this? Let me take you to the tool. Okay, so for that, what you have to do? First, you have to go to sound recorder on your laptop or whatever the thing is, and start recording. So let me give it a try. Wait a second. So I will try. Hello. Hey there. Okay, I told hello, but then hey there, I tried. Let me just play it. Hey there. Okay. So here is the recording. I will right click, show in folder. Here it is. I will copy this. Okay. See, I will copy this and I will move it to. Wait a second. I will go to MATLAB. Can. Okay. So in MATLAB, do you see here the current folder on left side? So here somewhere I will paste it. Okay. Then it has named some recording 6 M4A. I will rename this. I will rename this as uh, voice. Okay. Voice just to, I will, that's a intentional type of VOIS. Okay. Dot M4A. Okay. So now let me try it here. So how do I do this? Yeah. Okay, 1 second. There's some issue. Okay, okay. So audio read your file name. You have to give here. What's the file name? VOIS dot M4. Extension is very important. It has to be there in the same folder that you are pointing to, so that you don't have to give the path. Otherwise, you will have to give the path. It returns two things, by the way. Your voice, yes, and what sampling frequency it is being read at, so that when you play, you got to play at the same sampling frequency. Okay, so how to read it out, by the way? For that, first thing is, let me just run these two lines. Okay, let me just run these two lines. Right click, evaluate selection. Okay, and here can you see on this side? So the sampling frequency is 48,000. Okay, that is the sampling frequency. And you can see there are two dimensions here. So it is about 2 second video. So around 99,000 samples are there. And then that is stereo. Okay, there are two, there is mono and then there is stereo. In stereo, there are, it's a two-dimensional array that has got created. Okay. Now let me run this thing for you. So to run it, what you have to do is you have to give S, that is the signal that we have read. Okay. So should I double click this so that you want to see the signal here? You can see here the signal has so many values. Okay. Should I show you? Wait a second. Now let me just show you the signal. How does it look like in time domain? Okay, so plot, PLOT, uh, S. Well, simply I am not bothered about the x-axis. I'll simply use a plot and I will just show you, how does the signal look like. Okay, can you see this? 1 second. Here you can see. Hey there, right? Hey, pause there. Before hey also there was a pause. After there also there is a pause. So many samples here and there. Okay, that's my time domain. I cannot recognize anything in time domain. Okay, that's why we hate time domain anyway. Okay, but I can hear in time domain only. Now let us talk uh, sound. Let us see how to hear this. For that, what I will have to do is I will play sound s comma fs. So this is the fs that system returned to me, that is 48,000. So here I will type 48,000. So let me just run this thing now. Okay, I will remove this plot anyway. I don't need it. So I'll comment it anyway. So here evaluate select. Hey there. Okay. So did you hear that? Hey there came in. Okay. Now, what's the deal with the sampling frequency? Now, I want you to, appreciate the role of how many samples you play per second. How much, what role do they play? Now, 48,000 was the value, right? Now, let me change it to 55,000. That means now, instead of my standard FS, I am running it at 55,000 samples per second instead of 48. Now, let me run it once again. Okay. Let me run it once again. Hey there. Did you see the sound variation? I sounded like a chipmunk there, right? You remember in those cartoons and all, whatever they would come, strange sound, we wondered why. Okay, this is the reason, okay, because the way they are being played, right? Have you seen those Charlie Chaplin movies? The way he's moving very fast. Okay, that is because, it is being played at higher samples per frame. Now, shall I go for 60? I will go for 60,000 samples now. Okay, and I will run it once again. And you can see, hey there. Again, it is sounding different. Now, if at all I run it at 35,000 samples per second, again, it's going to be a different thing altogether. Hey there. See, that was very, droopy kind of thing. Okay. So, that's what sampling is. So if at all, every individual, the way his sound is recorded, if at all we play it at a different sampling frequency, it's going to sound different. Okay, anyway, that was cool. Now, what we'll do, we'll just is, do this exercise. The intention is to record an audio, see it in time domain, then afterwards, let us see its Fourier transform. Okay. So this I will comment because it will keep on playing. Now I would like to show you the Fourier transform. I will just see 1 second. We will just see 1 second of the audio. Okay. So from which second should I see? That's what I'm in a dilemma. Okay, because in first second there was no voice at all. Voice started only in the mid, right? So should I wait a second? Let us observe this. Eval selection. When did the voice start? Voice started around somewhere mid of it. Okay. So that's why. Anyway, let me play 1 second. So what I will do is here I will write 48. Okay, okay. See here I have chosen 48,000 samples here. That means I will like to see the Fourier transform of first 1 second of the audio. Okay, and let me just plot it to you here. Okay, so there I have plotted it, and let me just show you how does the plot look like. Wait a second, it has not popped up here. I think once again. In MATLAB. Okay, some bracket, some error has popped. Okay, okay. Oh, wait. Yeah, there is an error. Okay, probably I missed on one bracket here. Did you see this MATLAB? It gave a nice error. What did it say? Mismatched delimiter. Okay, so I even asked me, should I put it? And I have agreed. And there we go. Right click, evaluate selection. Okay. Here, I'll just show you 1 second. See, did you see in the previous program that I had shared, right? I had used a spooky command, fftshift. Here I have not used FFT, I simply used FFT, the Fourier transform. Let me just show you what's the utility of FFT shift also now. Okay, there you go. So 1 second, there were 48,000 samples. So from 0 to 48. Okay. Usually we want to see the Fourier transform centered around 0. Now this is 0. And here there is a replica on the right side. Okay. This is very unlikely. Usually you should start from minus pi by 2 to minus pi to pi. Minus fs by 2 to fs by 2. That is why, but this is not a soothing read. That's why what I will do here is I will use fftshift. Okay, what fftshift does is it lets me plot from minus fs by 2 to fs by 2. For that, what I'll do, I'll put one more bracket here, then an fft shift. It doesn't do much. Okay, it is just for, it's a visualization thing only. Okay. Now, okay. Again, it is asking. Oh God, I think. Okay, one more bracket. Okay, fine. Hmm. Okay, well, we could execute this, and here is my graph. Okay. Now can you see the graph? Now can you see the graph? Okay. So I was telling, okay, I need to adjust now my x-axis. X-axis still from 0 to here. So let me again go back to the program. Okay, so where should I do this? Okay, I will define x-axis. Okay, something like ax equal to minus fs by 2 colon fs divided by 2 minus 1. Okay. And here my x-axis I will type ax, which is my x-axis, and then this one. Let me try my luck if at all I get it right. Okay. Okay. See here, there's a yellow coloring. It's indicating that I should end this with a semicolon. Okay. For some strange reason, you find out what is it. Okay. Yeah. Now I am running it again. And here we go. Okay, can you see the image? Wait a second. Yeah. Okay. So here you can see 44 or 48,000 was the sampling frequency. So it is starting from somewhere around minus 24 to plus 24 from 0. Okay, from 0, and you have this thing. So do you see this one thing which we are supposed to make an observation is from 0, where does the frequencies lie? Two things, let me tell you. Remember, when we are talking about pre-emphasis and de-emphasis, I told you, frequency voice usually, most of the frequencies lies in the cutoff is usually something like a 3.4 or a 4. Okay, you can see here. Okay, so this zero point 0.5 here is actually 500. Okay, so this particular number here is actually 25,000. So this zero point 0.5 is actually 5,000. 0.5 into 10 to the power 4 it is. Okay. Let me delete the comment. Okay. Clear all my drawings. Okay. And so one thing is, you can see from 0, okay, at 0 there is no DC. So my voice no is something like this, and then afterwards decaying slowly, and there is nothing much in the higher frequencies above 4,000 because it was purely voice, and there is some fan noise in the background. Okay. And second thing is, you can see the gradual decay in the higher frequencies. Had it been a music, right, you should try to the music video. Okay, and you will find some of the peaks here. Okay, to preserve them only there was pre-emphasis. Okay. That is one thing. Second thing is, you can see whatever you get on the right side, no, something similar will be there on the left side also. And again, from minus fs by 2, minus fs by 2 to fs by 2 on the right side. Okay, that's it. Now I will show you one important concept called as filtering. Okay, I will tell you about filtering. Now in filtering, you have been using filtering in AM and FM. That is why I thought let me address this. So for filters, now what you do? Say I want to retain only this particular piece. Say I want to retain only this particular piece in this entire spectra. I want to remove everything below this value and above this particular value. Retain only this particular peak. Now, how should I do it? Then, for MATLAB, we have something called as filters, for which 0 is a 0 and your fs by 2. This turns out to be 1. Okay. And this point here, suppose I want to pick everything up to this particular value here, then I should mention my cutoff frequency is 0.5. Okay. If at all I want to retain only from here to here, so probably that will be something like 1 is a 25, zero point 0.5 is a 0.2. Okay. And this something, it seems to be something like a 0.8 to something like this value seems to be a 1.8. Okay, you try this thing on your computer. Okay, you try this thing. Now let me show you how does a filter work. Okay, so in my program for a demo, I have chosen a filter. Okay, so how to use a filter? By the way, filters come with this particular commands called as fir1. Okay, then you got to give a very nice order. Okay, in did you study first order filter, second order filter? This is a digital filter. You can go for any higher order also. I have chosen 41 for some reason. Okay, now I will give, I wanted the value somewhere from point 0.1 to point 0.2, right? Somewhere like that. What number did I tell? Something like 0.8. Okay, I wanted number from 0.8 up to, it's a band pass filter. I will use a band pass filter. Okay, 0.8 to something like a 0.08, sorry, 0.08 to, or wait, from 0.1 to 0.2. Let me keep it simple. 0.1 to 0.2. Okay, now that's a filter. Okay, so this one I will remove. That is, I was trying a high pass filter. That's a filter. Okay, cutoff frequencies are mentioned. Let me just run this thing here. Okay, evaluate. Then there is a command called as freqz b. Okay, let me run this thing now. Okay, and let me just show you what has happened. Okay, so let me share you the image. Okay, now you can see here, there you go. See here you have a band pass kind of filter, a band pass kind of filter, which is allowing a band in this particular thing. This entire thing, right? This entire thing is my 0 to pi. Out of this, which is normalized one, I have chosen this particular band. You can see the lower frequencies are also suppressed. Okay. See, lower frequencies suppressed, higher frequencies are also suppressed. In between these all frequencies, you can see in the center, they are being allowed. Okay, that's how we choose it. If at all I didn't, okay, now let me, this phase we are not interested for the time being. Okay, so let me show you what's the impact on my response. Okay, let me, by going back to this program, and here I will now sample my signal 48,000, right? Okay, okay. Hmm. Shall I run this? I did. Here to the sound, okay? Hey there, I use hey there, and it sounded a little less. Okay, something has happened. Okay, for that, what has happened? Sound was clearly different. Okay, now let me plot you the the graph now of the filtered version, and you will be convinced. Okay, now this one second, one second. Let me run them together. Okay, I don't know what screen you are. Okay. Now, let me run both of them together. I was telling, okay, here. Hmm. X-axis, I will use the same AX here. Okay, forward X-axis. Okay, yeah. I'm plotting both the graphs, one above the other. Or I thought so. Wait a second, it's not what I was anticipating. Copy, okay, wait. Okay, now we are good. Okay. Uh, yes. One second. Okay, S in place of S, I should type SF. Okay. So it's very easy when your faculty gives you a program or chat GPT gives you a program, you run it without any errors. But then can be tricky when it actually happens. Okay. Here, now did you see the screen? What has happened? Wait a second. Let me share you the change what has happened. Okay. Now can you see? First, when you saw, you had some frequencies here. Uh, you can see earlier you had some frequencies here and you had frequencies here also. After filtering, what has happened is this entire section, the frequency has been removed. Okay. So this section you can see frequency completely removed on right side. See, this is a filter. Okay. You are supposed to see only from 0 to the right side. Do not see this left side part at all. Okay, we are not bothered. Okay, got this particular thing. Now, can I show you? Now I will change the filter. I will pick everything from 0 up to 0.3 for a change. Okay, I will try that. Let me just show you. Okay, so I want you to try out filters also and check how it sounds different. Okay, so here. Uh, One second. There. Okay. Now I will make a slight change here. In the filter, I choose the band pass. Right now, what I will do, I will remove this. I will simply keep a 0.15. Okay. Or a 0.1. What does that mean? That means it now takes only zero point 0.1 of 48,000 divided by 224 up to 0.24 up, that means up to 2.4 kilohertz only it will retain. Rest all it's simply going to remove. Okay. So now let me run this thing and hey there. Here is the graph now. What's the change? You should be able to tell me. Now this is my change filter and you can see it is having all the values from not red. Let me choose blue. Okay, it's having values only up to 0.25. Afterwards, the values have been suppressed. Okay, that's what a filter is. Okay, so that was about our trial on audio. I hope you also try this tiny program, record your voice, change the frequency, hear to, how does it sound like, increase the sampling frequency, reduce the sampling frequency, explore what those two dimensions are doing, what's mono, what's stereo, take some audio file, okay, any some song, try filters, try an equalizer of your own, try to do from an audio file, convert it into karaoke file, right, where you put your voice instead of nice voice, okay, by suppressing frequencies below 5K and keeping all frequencies above 5K. Okay, try all those things. I will put this piece in the comment section for your reference. Okay, so thank you.